Welcome to the Solubility Equilibria video. By the end of this video, you should understand what it means for a solution to be at equilibrium. You should understand how the solubility product constant, or KSP, can be used to describe the solubility equilibria. And you should be able to calculate KSP from solubility info and go the other direction, calculate solubility from the KSP value. Before we dive in, let's just refresh our memory on some important vocabulary. A saturated solution is a solution in which the maximum amount of solute has been dissolved in a given amount of solvent at a particular temperature. This is typically measured in molarity or moles per liter. Sometimes you might see grams per liter as well. So it's the maximum number of moles of solute you can dissolve per liter of solution. Notice I've said at a given temperature, it is temperature dependent. An unsaturated solution is a solution that contains less than the maximum amount of solute that can be dissolved at that temperature. So on the practical level, in a saturated solution, when you add more solute, it won't dissolve. It'll just sink to the bottom. Whereas in an unsaturated solution, if you add more solute, it will continue to dissolve. Let's look at a quick simulation of this. Here I have some water. I'm going to start adding solute, in this case potassium permanganate, by sliding up this slider. Notice that it's continuing to dissolve. We know this because it's not sinking to the bottom until I hit the saturation point. At that point, I've dissolved the maximum amount of solute that can dissolve in this amount of water at this temperature. So any additional solute would just sink to the bottom. It will not dissolve and will not join the solution. Once we've achieved a saturated solution, that solution is at equilibrium. The rate at which ions from the solid are dissolving into the solution is equal to the rate at which ions in the solution are crystallizing and rejoining the solid. Therefore, we're at equilibrium. There's no net change in the number of dissolved ions. However, there is still a dynamic process of dissolving and crystallization occurring. Like any equilibrium, we can describe it using a K value. The K for a solubility equilibrium system is called the solubility product constant, or KSP. This is the equilibrium constant that describes the solubility of a salt. Let's consider the dissolving of calcium hydroxide. First, we write a dissociation equation showing what happens when calcium hydroxide dissolves in water. And then we can turn that into a K expression. Recall that K expressions never include solids, so our KSP expression will be KSP equals the concentration of calcium times the concentration of hydroxide squared. Squared because of the coefficient of 2 in front of the hydroxide. Because dissolving equations always start with a solid, we'll never have a denominator in a KSP expression. If you find yourself writing a denominator, you've probably done something wrong. Here's a few to try on your own. Pause the video here, write dissociation equations for each of these, and then write K expressions for each of them. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Notice that I started with dissociation equations for each, and then I wrote K expressions using the coefficients as my exponents in each case. Also notice that none of them have denominators because in each case we started with a solid. KSP values can be really useful in comparing solubility. Consider these three salts with their associated KSP values. Which of these salts is the most soluble? In other words, which of these salts is able to most dissolve in water at 25 degrees Celsius? You should have determined that calcium carbonate is the most soluble salt. Notice it has the largest KSP value. That means that when the solution is saturated, there are more ions of calcium and carbonate in solution than there are of the other two salts. A higher KSP value indicates a more product-favored dissolving process and therefore a more soluble salt. Now let's look at how to calculate KSP given solubility data. Copper bromide has a measured solubility of 2.0 times 10 to the negative fourth molar at 25 degrees Celsius. Calculate the KSP. As a first step, we need to write the dissociation equation. So we've got copper 1 bromide, CuBr, that's a solid, and when it dissociates, it will be in equilibrium with copper plus and Br minus, both aqueous. From there, we write the K expression. So KSP is going to be equal to the concentration of copper times the concentration of bromine. Again, we don't include the copper bromide because it's a solid. Since we know how much copper bromide will dissolve in 1 liter, we know the concentrations of both Cu plus and Br minus, so we can plug them in to solve for K. We've already been told that at 25 degrees Celsius, 2.0 times 10 to the negative 4th moles will dissolve in every liter. Therefore, our concentration of copper will be 2.0 times 10 to the negative 4th, as will our concentration of bromine. Doing this math, we find that that means our KSP is 4.0 times 10 to the negative 8th. Recall that KSP values are unitless. Here's one to try on your own. Pause the video here and do this math. When you come back, I'll reveal the answer. As a hint, notice that I've given you the solubility in grams per liter, so you'll have to do a conversion before you start. Welcome back. Here's what you should have gotten. Notice I started by converting my grams per liter into moles per liter, so I had an actual concentration value to work with. Then I wrote my KSP expression. Welcome back. Here's what you should have gotten. There are a few tricks here. First, we had to convert our grams to moles, so we actually had a molarity instead of grams per liter. Then we write our dissociation equation and our KSP expression. But notice there's a bit of a trick here. Since 0.33 moles of AlCl3 dissolve in every liter, that means we'll get 0.33 moles of Al in every liter. However, for every aluminum in aluminum chloride, we get 3 chlorides. Therefore, our chloride concentration will be 3 times the aluminum concentration. Therefore, I need to plug in 0.99 for my chloride concentration. I also need to cube it because the KSP expression tells me to do so. We can also go in the other direction, calculating solubility from KSP. Here we're given a KSP for AgI and asked to calculate the solubility. So first I'm going to start by writing the dissociation equation. So AgI is in equilibrium with Ag plus and I minus, both aqueous. Then I'm going to write my K expression. So KSP is going to be equal to the concentration of silver times the concentration of iodide. In this case, since it's a 1-to-1 ratio between Ag and I, we can call both of those X. So our KSP is going to equal X times X, or X squared. We know that the KSP is 1.5 times 10 to the negative 16th. So using that, we can solve for X by taking the square root of both sides. And we get 1.2 times 10 to the negative 8th. Now, since this is a solubility, we do need a unit, so it's going to be moles per liter or molarity, whichever you prefer. Here's one to try on your own. Here you're asked to solve for the solubility of PbBr2 in water at 25 degrees Celsius, given the KSP. Recall that we used X to stand in for the concentration of each ion, but notice in this case, instead of a 1-to-1 ratio, you have a 2-to-1 ratio, so you'll have to consider that when writing out your equation. Pause the video here, and when you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. First, I wrote my dissociation equation. Then I wrote my K expression. In this case, since I called the concentration of Pb2 plus X, the concentration of Br minus must be 2X, since it's going to be twice that of lead. I then also square that to give me 4X cubed. Solving for X, I get 0.012 moles per liter, meaning that in every liter of water at 25 degrees Celsius, I can dissolve a maximum of 0.012 moles of lead bromide. That brings us to the end of this video. Let's review our goals. First, we looked at what it means for a solution to be at equilibrium. Recall this means it's saturated. Then we looked at how the solubility product constant, or KSP, can be used to describe solubility equilibria. Then we looked at how to calculate KSP from solubility info and how to calculate the solubility from the KSP value.